So today we're having a Meow seminar with Alexander Tesch, who will tell us about the very latest and hottest news in pseudo-Boolean solving. So please, Alex, take it away.
Yeah, thank you for having me. Thank you very much for the invitation. So, yeah, hi, welcome to the Meow seminar. So today I will talk about the current developments in pseudo-Boolean optimization, which bothers the whole group, I would say, also problems in pseudo-Boolean optimization. And I will show you a few results or a few ideas and developments that we do in our LazyPB solver, and that might spark some interest for you to gather some ideas. Huh? So yeah, maybe like a brief outline. So first, I will just that we are all on the right page. I will still have a brief introduction maybe to pseudo-Boolean solving, so that we are all on the same page. Then I will dive more deeper into conflict analysis with different approaches, like which resolution approach do we have in conflict analysis, and do also some improvements and comparisons of current approaches that we have. There are some ideas, and also I present something according to calculation methods. There's also an open problem that we have. And I will also deep dive a little bit more into Boolean optimization and duality, which is a little bit new in the context of Boolean optimization, to integrate ideas from p-duality. And mostly this will be probably in the second part of the talk, because it will deep dive a little bit more into LP theory. And in the end, I will conclusion and open problem. So, okay, maybe let's start very brief. Probably will be not so interesting for many of you because you know most of this. Okay, what problem are we dealing with? We're dealing with Boolean variables like x1 to xn, all can be either true or false, and we have a set of linear constraints that are this type of form. In principle, we just deal with integer coefficients, so the coefficients of the variables can either be integer, and the right hand side of the constraint can also be integer. So, and goal, what we want to do in pseudo-Boolean, basic pseudo-Boolean solving is that we want to compute a feasible solution to the system of linear inequalities, or to prove that non-existent. We very often convert this form into a normalized form, which can be also of computational interest sometimes. So to have non-negative coefficients in your problem. So that there we consider a literal form, where literal can either be variable itself or the negation. And we can write it in a very similar form. The coefficients are all positive. And we also have a positive right hand side if the constraint is not native or redundant. And if we give already a little bit this LP interpretation, is that this literal version can be interpreted as an extended mathematical space where we just double the type of variables and have a linear transformation on them. So this again projects back into the original space in an exact way. In principle, this literal form is nothing else than just an extension of the Okay, so in pseudo-Boolean solving, we're dealing with a cutting plane proof system that mainly consists of these three inference rules. We have the literal axiom, so it must be non-negative. We have addition, where we can combine two linear inequalities according to certain multipliers and add them up. And we have division, where we can define a divisor and we can divide the constraint and round corresponding coefficients on the right hand side. So, in principle, this addition plus division, this yields quarter-Gomorrhic cuts, which is mixed programming, a very, very popular class of cutting planes. So if we combine these two, like in one rule, we can also get like the very famous quarter-Gomorrhic cuts, which also give a proof systematically to solve mixed integer program. We apply them continuously after each other and consider the half of quarter-Gomorrhic cuts in a repetitive manner. So, okay, what is a cutting plane proof? Is we take the set of constraints that we have from our original model, and we use these rules in order to generate new constraints. And we want to derive, and let's assume the instance is unsat. We derive a trivial infeasibility as a last constraint, as a consequence of all of these inference rules that we used in order to generate new constraints. And of course, every constraint that is generated must be a consequence of the inference rule that we have generated.
This should be 0 greater equal 1, right?
This is true. This is obviously feasible, and it should obviously be 0 greater equal 1. Obviously, that's fine.
Okay,
yeah,
that's double checking. Small typo.
This is a small typo. It should of course be 0. Yeah, when we derive this supposedly infeasibility, so this then M is the proof length. So, okay. So of course we want to use this proof system to generate fast answer proof that have a small proof. Just to compare to standard set approaches where we normally use in satisfiability solvers the resolution proof system, we can also have the extend this by an extension rule. Just to compare to these approaches, it's basically like that we know that the extension rule proof system is consists of the resolution rule plus the extension rule, and we know that CP or otherwise that CP dominates resolution. We can simulate resolution by CP. Yeah, very common result. There also exists exponential separation because we know that pigeonhole formulas you can solve in polynomial time by the cutting plane proof system, but not by the resolution proof system. On the other hand, we know that extended resolution can also polynomially simulate cutting planes. That means extended resolution is at least as good as cutting. But the problem is that in practice we do not know how to make good use of the extension rule. But in cutting planes we have maybe a little bit of better intuition on how to make a good use of this cutting plane proof system. So that means right now, in order to get better proofs for hard formulas, in the subworld maybe as PHP, by pigeonhole formulas, maybe CP is a good way to solve hard formulas that we do not know how to solve them in the subworld right now. So yeah, in general, it can be said the CP cutting planes and extended resolution have exponentially shorter proof than resolution on certain formulas like PHP. And I think, to the best of my knowledge, CP, it's an open question whether CP can actually simulate extended resolution. This must be an open problem as far as I know.
I think probably we have examples of extended resolution being exponentially stronger than I would guess, but I would need to check. I think it's probably known that extended resolution is exponentially strong, but need to check.
Anyone know from the? Because as far as I know, it's actually an open problem. Because also, I mean, extended Vega simulates cutting planes. Vega simulates cutting planes.
Extended Frege and extended resolution are polynomially.
Yes, but I think it's also open whether Vega can actually simulate.
Oh, we should see if the click coloring formulas for extended Frege. Yes.
Also, in the original paper of Cook, there was also no example found that exponentially separates them. It's the best of my knowledge.
We'll have to take this as homework.
We have to take it as homework. I think it's still an open problem. But it's conjectured that this does not hold. Yeah. So direction. Okay. So of course there are other inference rules that we also standard-wise use in pseudo-Boolean solvers. So there's saturation. So we just take the minimum of the right-hand side and each coefficients, which must typically hold for any linear constraint. And this can also be simulated by division if the coefficients are linear. Further, we have like cardinality conversion, which is the Alena solver in the original solver paper. They use this rule where we just look how many of the literals must be satisfied at minimum in order to satisfy it. Then we can just convert this constraint to this, and this is an inference rule. So, of course, this can be useful because cardinality constraints are much more cache friendly because we don't have to store the coefficients, and this can be useful. But also the cardinality conversion can be simulated by. Then we have, of course, weakening, so where we just pick one literal and we can weaken the coefficient away, and at the same time weaken on the right-hand side. So, and weakening can be simulated also by addition and literal. Okay, then we have lifted cover cuts, which is maybe a little bit new in the context of pseudo-Boolean optimization. So we take an original constraint and we can extend it by such a form. And here, S denotes the base clause that must hold according to this constraint. And this base clause we can extend by additional literals in order to strengthen this constraint. And the way we compute these extension here is by solving an optimization problem repeatedly. I will come to the exact computation a little bit later, but just take it as an inference rule. We compute these lifting coefficients in a repetitive manner. So there's an optimization algorithm, how we can ensure that they are actually feasible for the problem. And we can interpret it a little bit in a way that, okay, we pick one literal that is not in this base class. There might exist another one that is outside of this clause, and if we set this to 0, then we can actually strengthen this constraint by exactly such a PI that we have to compute in order to use it. This is very similar to an idea that was already presented in one earlier paper once in pseudo-Boolean optimization. But these ideas, they exist in the MIP community already for quite a while. So this cover cut is a standard tool in mixed-interp program.
So the way to read this, because I see it in greater equal form for the first time, I think. So like either you start from knowing that this inequality is true, and then you round it to a clause like it will be true that the sum of the literals will be at least 1, I guess. Do we know that? Like sum of the LIs in S is at least 1?
So
we know.
We can always derive such a constraint.
This we already know, and then you say, but lots more of the LIs, either lots more of the LIs are true, or these other guys contribute.
Let's say, for example, suppose I have one that is not in the cover, but that has a very large coefficient. You know, but now I do not take this in order to satisfy the constraint. I assume it's 0. Then actually, from the set that I have chosen, actually much more must be satisfied than only 1. Yeah. So in this case, this has this implication that we can strengthen this by some amount, and this some amount needs to be computed first by an optimization algorithm or by a heuristic. Yeah. So this is kind of the interpretation that we do, and we can do this then in a recursive way, in an iterative way, in order to then lift the other ones into the constraint. So what we can do is we can determine a sequence of these lifting elements, and we lift them one by each other into the constraint. So, but in general, the exact computation of these lifting coefficients is NP-hard already, but there exist still fast dynamic programming algorithms how you can do it, or fast heuristics that can also do it in polynomial time. And I will think about this a little bit more later. So then there's also something that has not been investigated so much, I guess, yet in pseudo-Boolean optimization are click cuts. But probably people have seen this already a long time before. Also in mixed-interp programming, it's a very common concept. We always have these binary clauses that we can also derive from real constraints, pseudo-Boolean constraints. And if we have a set of these clauses, a set of these binary clauses, and they hold between the click, that means between all elements in this set S, then we can derive a much stronger constraint, which is the so-called click constraint. So if this pairwise needs to hold between any pairs ij in this set S, then we also know, okay, if we have to take at least 1 in each of these sets, then we in total have to take at least S minus 1. So these are click constraints. If you would turn it around in a lower equal to form, it basically means that okay, the sum of the negations must be smaller equal to 1, so that you can take at most 1 negation. Yeah. So so very often also in MIP solving, these click cuts are derived in a pre-processing step, because it's just something that's good to do. And you can also simulate these click cuts also by addition and division. This is, I think, also how Cook does it in its original proof of the pigeonhole proof. So you can derive such cuts. But it's one of the few inference rules that reasons over multiple constraints. And I think we need much more of these type of inference. So, and I think it can actually be a very strong rule, because I will mention this also later in the end, that, for example, for pigeonhole principle, the clicks that we can derive from there are actually very simple to detect. I mean, you can just like greedily add them one into the one element in each other, and then we can derive such clickers very easily. So maybe this can be like a little bit of a missing part on how we can make CNF computations better for pseudo-Boolean solving. So, but of course, also max click, you find always the maximum click is actually hard, but they are also very fast. Okay, then there's another inference rule, the mixed integer rounding cut, also introduced by Maxi. And the rule looks a little bit of a complex formula, but in principle, it's a strengthening rule. It's the strengthening of the division rule, where we can, in the set I2, derive stronger coefficients. Because we can use this stronger expression here. Because in the division cut, we would always round up, but here we can use the rounded down plus this fractional expression here, which is a little bit stronger than the normal division cut. So, and in principle, near cuts for the same divisor are always stronger. Yeah, we can prove this. And but we normally with fractional coefficients, and if we want to use it for BB solving, except BB solving, then we need to multiply this by this factor here in order to get into the proof. So we can make them integer in the end, but the coefficients may blow up. So, okay. Then, of course, how do we solve Boolean optimization problems is by conflict-driven clause learning, which is an adaptation of by conflict-driven constraint learning, which is an adaptation of conflict-driven clause learning from SAT. And works basically that we for unit propagation, where we might infer that some of the constraints is infeasible. This is the case, then we want to learn another conflict constraint from the original conflict constraints, and then add it to B. We get the starting level of this constraint, and if this is like -1, which means that it's already falsifying at the root level, then we can return answered. Then we have proven this to have infeasibility proof. Otherwise, we backtrack to the decision level in order to continue the search. But because we have added this conflict constraint that is now asserting at this back propagation level, we will make another decision and not run into the same conflict. So otherwise, if we have if the conflict constraint is empty, then we check if all values are signed, then we return that. Otherwise, if we take an unassigned, get unassigned literal and then assign it and then continue. And CDCL consists mainly of 3 parts. This is unit propagation, conflict analysis, and variable selection. But the main point of interest is conflict analysis, with very important on how to do this conflict analysis to generate strong constraints so we can generate fundamentally strong. Okay, then this was the small introduction. Then let's turn to conflict analysis. Okay, so how does conflict analysis work in general? The main algorithm is as follows. So we are given a conflicting constraint from our constraint database. We want to learn a new constraint, learn that is asserting at an earlier decision level, than the current conflict. So initially, we initialize learn as the actual conflict constraint. We extract. I mean, there's slightly variations of this. I'm just describing the general algorithm that works, but of course you can modify it a little bit to make it more efficient. But in principle, you would get the latest false literal from learn. You would check if the decision level of this is actually 0. Then, then you would know that that the conflict constraint is already falsified at the root level. And then you can return answer. Otherwise, if this is not the case, then we can backtrack to the position in the trail where the literal occurs. And then we track the reason constraint of this of the falsified literal, and we make the conversion of the learned side, that means on the conflict side, and on the reason side. So what this conversion is very adaptive to the respective method on how we actually do conflict analysis. Then we combine them in a certain way, mostly we add them up in order to update the learn constraint. And if the learn constraint is asserting at the level, decision level -1, then we return the learn constraint. And this whole process we can repeat and until we either find that the constraint is answered or that we find a unique implication point. One is a unique implication point. And it depends again on which definition of a unique implication point. So the main question is actually how to perform this step. So how do we convert the reason side into another constraint, and how to convert the conflict side into another constraint, and how to add them up in order to derive a new strong constraint. So this is the main input. There are many different resolution approaches for this. So in the original rounding subpaper, I just called this round-to-one resolution. So assume we're given a constraint C, a partial assignment O, and the pivot literal LJ. So what we normally used to do in the original paper, again, there are slight variations of how to do this, but in principle, we can do partial weakening of all non-false literals in the constraints, and we can weaken them to a multiple of coefficient of the pivot literal. Then we can do division by the coefficient of the pivot literal, and that's it. That's the conversion. So what we have in the end is that for the new constraint, the coefficient has a coefficient of 1 for the pivot literal, and it makes it easier to actually add them up, because if the pivot literal and the one constraint has a 1, it has another in the reason constraint also has a coefficient of 1, and you can just add them up, and the literal will be resolved. So just a small example for round-to-one, we have let's say we have this constraint. So the box 1 is the pivot literal. Let's say it propagated to true. Yeah, and be on the reason side, and let's say the red ones are the ones that are falsified. So constraint is propagated. So if we now do round-to-one conversion, so what we would do is that we look at all the non-false literals, which would be in the front, that we round them to a multiple, which leaves partial weakening would be just like would weaken 7 away to 4, because 4 is a multiple of 4. So we weaken this away, so we subtract 2 here. And then we would divide by 4, which would leave this constraint, and this simple example for. In the end, it's again a question how if we ever should do it, but in principle we can do a round-to-one approach on the conflict side and on the reason side. If we just add them up, it will cancel out the resolution network. So of course there are other approaches that might not perform the round-to-one operation on the conflict side and just only on the reason side, but I'll leave this for the solid stuff. So then there's mixed integer rounding resolution, which in principle works exactly the same. The way we do weakening is also up to current research still, but in principle you can also weaken away all the non-false literals to a multiple of the pivot coefficient. And then you can do mixed integer rounding division also by the pivot coefficient. And then you should also multiply it again in order to also, again, small example, we have this constraint where they equal to 0. So we would again do partial weakening on the non-false literals. That means L2 would get a multiple 6 is a multiple of 3. So we get this weakening by 1. And then we could do here normal division, for example, would be, if we divide this by 3, would be this. Then mixed integer rounding division would be slightly stronger, which we get at 2.5 here. So these are these fractions that occur in mixed integer rounding, which you see already is stronger than the normal division. And you could then make it integer by multiplying this by 2, and you would also get a stronger constraint that is also integer. And this is the power of mixed integer rounding, because the coefficients are always strictly, at least as strong, can be strictly strong. So, and you can do the resolution in the same way that you possibly. Okay, but there are a few challenges with this. So, of course, as I said, it strictly dominates division for the same multiplier, but we get fractional cuts, and we need to multiply them still by some integer. This might blow up the coefficients. We need to really take care to get them down, and may have some immediate steps where we bring these coefficients down. Okay, and yeah, so there's also some. So now we go to lifted cover cuts. We will write a paper about this now, right? But this I implemented also in the LazyPB solver. And let's say we have a constraint, and we have this rule. So how does it work? We have a constraint, a partial assignment in the p-Bool literal, and what we do first is to extract a minimal base clause from the given constraint according to the current assignment. If your constraint is propagating, then it would be the unit clause that is propagating the corresponding literal, or an implied clause that is propagating the p-Bool literal, or it is an infeasible clause that you can extract from the constraint. And then you compute the lifting coefficients, as I said, by sequential lifting or some heuristic. And in principle, you can approach in the same way. But again, you can vary this resolution step here a little bit. But one of the benefits of this approach is that the p-Bool literal by default has a coefficient of 1. So you can just take a multiple of this and add this to the conflict side. So because it will always have by default a coefficient of 1, which is very good to handle.
Suppose that you could actually have extracted a cardinality constraint, like not just a clause, but a cardinality constraint. Yes. Would you then recover this cardinality constraint because you would be able to lift some variables with coefficient 1?
Yes, it's possible, absolutely.
Would it happen, or would you need to be like lucky for it to happen?
But you can also get something better than a cardinality constraint. You can also get something with coefficient 2, and also, I mean, lift it exactly. But
yeah, I guess the question is like, would it make sense to if you already know that you have a cardinality constraint, could you use that as the base case of your lifting, or no? That doesn't.
I mean, you know that you have a cardinality constraint already. I'm not sure whether you would apply this procedure at all, because.
I mean, if you know that you can extract not just the clause, but actually a cardinality constraint. Say, like, you know, without like you know that instead of x1 plus x2 plus x3, one of them is true. You realize that, oh, but I could have thrown in, you know, x1 up to x4. At least 2 of them were true. And should you use that as the base case of your lifted cover cut? Or no, it doesn't make any sense because you'll discover x4 anyway.
Because it's a whole procedure. You will discover this x4 that you can lift in additionally. So that's the whole procedure. Maybe even more. No? Maybe it has even a higher coefficient.
Yeah, no. Yeah. Mm-hmm.
So yeah. So what you would apply is then sequential lifting. I mean, I want to describe a little bit how this computation of these lifting coefficients work. And for this, I will switch the sign for our constraint, because this interpretation is much easier for me to understand, and I think also in general to understand. That's why I will just switch to lower equal here. So in that case, the minimal base clause is not clause anymore. Actually, it's a minimal cover inequality. This is how it's called in operations research community. And you will extract this base clause. And then the question is, like, for every element that is not in the clause, you want to find such a coefficient such that if you add it into the cover inequality, is feasible. Yeah? The question is, like, how big can this beta become? Actually, what we, in order to see this actually quite easily, is you just shift around, yeah? You push on the other side, and then you get like this expression that beta j must be small equal to cardinality of S minus 1 minus this expression. Then the question is, because it must be in general, it must be feasible. You would say like, okay, then I minimize right-hand side, this expression, under the assumption also that Lj is equal to 1, because I think that I must hold, so I assume Lj is 1. And I try at the same time to minimize this right-hand side so that the beta j is exactly this expression, so that it's in general valid. Right? This leads to an optimization problem. So the optimization problem is in the end that beta j equal to S minus 1 minus, we maximize this so that this gets as small as possible. So you maximize this expression. So the sum of all the Lj that are in the cover, but under the original constraint of your original constraint. Yeah? Under the assumption, of course, that Lj is 1, so you subtract this Aj. Right. Okay. So, and this is just a knapsack problem in principle. You can solve it with dynamic programming, and then you get coefficient. So, as simple as that. And yeah, normally your data is integer, so you can solve it relatively quickly by dynamic programming. Knapsack problem. The same procedure can be repeated. So if you have lifted in the other one, you can assume that you have a whole lifting sequence and assume that the ones that are in the cover have been lifted already. You can compute the next lifting coefficient in the same way, just under the assumption that you maximize over the currently lifted, maximize the literals according to the lifted coefficient already, but the remaining procedure is exactly the same. You fix the lifting literal and you subtract the coefficient that it has in the original coefficient. And also a quite old paper that you can compute all the lifting coefficients for the whole constraint in quadratic. So you can resolve the exact coefficients in polynomial time. The coefficient of the whole constraint. So then maybe what I should also note is that these constraints are facet defining for the original constraint. That means they are the strongest possible inequalities that we can compute there. So they cannot be dominated by another. They can only be incomparable, but they cannot be locally dominated by another. Okay, then there are other faster relaxations for lifted cover cache. Some of them we have implemented already. So then there's this index method, which is much easier to compute, where you just compute the largest R coefficients in the cover according to the original constraint, and we just make an index comparison. The index turns out to be exactly the lifting coefficients, but this is a relaxation, so these lifting coefficients can be a little smaller than for the exact procedure. So, but they can be computed like quite fast, so you just need to sort. Sometimes they are sorted already by your data structures in your pseudo-Boolean solver, and then you can even skip this step, and then you just need to compare. So it's a quite efficient method. Then there's even simpler, I call it simple rounding, where you can compute it directly like this, or you can also have like extended covers. There's a good overview of a survey of knapsack polytopes, where you have a lot of approaches on how you can compute feasible cuts for a knapsack polytope. Here you can even, if you want to derive a cardinality constraint out of this, you can even just set this to 1, but this is bigger than the maximum coefficient. And you can compute it in linear time. So, okay, so these are feasible relaxations that might help you in fact. And of course, you can put a clear hierarchy between them. So the index method is stronger than simple rounding, and simple rounding is also stronger than extended cover. Whether this is practically true is a different question. But theoretically, in order to derive the constraint, you have a hierarchy between them. Okay, so just to make a small example maybe for lifted cover cuts. So we'll assume this is our original constraint. The red ones are set to false, and the middle one is our P literal. What we would do is we would expect a minimal base clause that needs to be satisfied here, given by falsified literals. So this is one of them must be true in order to satisfy the constraint. So when we have extracted this minimal base clause, we have a lifting sequence, which can be L1. If we want to lift in L1 at first, we have to compute this optimization problem, which is beta 1 equal to the minimum of those elements of the sum of the intervals that are already in the cover, which is L3, L4, and 5, such that the knapsack constraint, okay, it's not here, I guess. Oh no, okay, here I have a greater equal to example. I think I switched it in later. But in principle, okay.
Here it seems you have to satisfy all of them, right?
So here,
because you need it to sum to 6, it seems.
I think the example is 4, to be honest.
Okay.
Yeah, I think I changed it then later to the smaller equal to form, and I didn't recover it here. But in principle, the lifting coefficients are still right. So this one needs to be at 2, and this one also needs to be. Okay, maybe I will fix this on my revised slide. Okay, yeah, but still you can compare them also to the extended cover cuts or the rounded cuts, and you can see that, for example, the index cuts are as strong as the real lifted cover cut, but this one here is a little weaker because this here is lifted up. So you can see that the extended cover cut and the round cut are a little weaker than the actual lifted or index cut. Huh? Okay.
And in this particular case, this is the same that division would give you, but in general, the cuts you get are incomparable, or can you say anything about lifted cover cuts compared to what Algomori division?
Lifted cover cuts can not be dominated. They are locally the strongest that you can get. They are facet defined. So they can, either they're incomparable or they dominate. And you can also find examples for it. Even two meerkats, they can dominate meerkat. Mm-hmm. So this is also, I think, the distinction between the current approaches that we have right now. The other ones are not probably facet defining. There are, in the literature, you can find conditions under which, for example, even extended cover cuts, for example, can be facet defining. But in general, these conditions are neither satisfied. And right now, so locally lifted cover cuts are the strongest that you can get. There's also maybe the same time the weakness in them, because they might be locally strong. For example, meerkats, because you make this division on all the coefficients, are maybe more general, because you keep a lot of these coefficients in the constraint, while here you may throw out a lot of them. So that means we may derive like a locally very strong cut, but that maybe lacks generality. This we might have actually with meerkats maybe more, and this needs to be explored a little bit. Whether this can be good for certain.
So you're saying the lifted cover cut might speak about fewer variables, but it gives very much information about these variables. The meerkat might be slightly weaker, but it says lots of things about other variables.
The cover cut is probably the strongest explanation that you can get for this constraint in that moment. So that's and this trade-off needs to be explored between like from locality and more generality, but maybe weaker. Okay, so we can do like a few improvements of these methods. First of all, we have said already that like this round-to-one approach, if you do the weakening in the same way, is dominated by the mere approach because the coefficients can be stronger. And yeah, as I said, lifted cover cuts are facet defining for the induced knapsack polytope. And even the relaxations, for example, the ballast procedure, even they can be stronger than meerkats. There are also examples where you can show this. So even like the relaxations can somehow be strong because you have this strong local properties somehow that you can derive from. So even relaxation can be better than the meerkats, but doesn't have to be. Yeah, but they exist example where this can be. That's why this relaxation, I think, also work actually quite bad. At least the Ballas index methods works quite good. But of course, which is also to be noted, lifted cover cuts note not all the facets that exist for a polytope. That means not all the facets that a polytope has are lifted cover cuts. So it's just a particular class of facets that we can derive. But there are other facets or other strong inequalities that cannot be derived as a lifted. Okay. So yeah, and maybe to derive this goal from a more mixed integer programming type of perspective is that we could look at the two polytopes, learn and reason from these two cuts that we consider in conflict analysis. What we actually want to do, that we want to compute strong cuts for the intersection of this polytope. Yeah? Because right now, and yeah, how do we do this? Yeah, probably by getting strong constraint from each, or strong facets from each of the polytopes. Yeah, this is what we exactly try to do with lifted cover cuts. Lifted cover cuts are strong for each of the polytopes we learn and we reason, and we try to construct a strong constraint out of these two constraints. Because the general idea is we cannot produce strong constraints out of weak constraints. That's why we should always use the strongest possible constraints that we can derive from each of these polytopes. So, okay, so this is the general. Okay, so like a very simple improvement that we can do, and I think that we have horribly wrong right now in pseudo-Boolean optimization, is that we can improve the rounding step by a very trivial method. So assume we have a division cut that is CD, where we just divide by D, where the right-hand side is without a lot of general decay. Then there exists a cut, the alpha, where we define like this, with this factor of mu, where that we define like this, and then I claim that this cut is dominating the other one and can be strictly strong. Yeah, why is this? I mean, you can always say like let's assume you have a factor on this constraint, right? So when does it give an improvement? So yeah, only when you can round a lot on the right-hand side, then the constraint gets strong, right? And let's say you fix this to a particular k, and then you can go down as much as possible because the left-hand side is just monotonely decreasing or constant. Yeah. So you can actually get smaller coefficients when you set it to these values. So you can get smaller coefficients on the left-hand side. Again, you get stronger constraint for the same right-hand side. Yeah, does it make sense? So I think whenever we do division, actually we should use these cuts, not normal division cuts. We should not divide by an integer. But of course, you can, I mean, I just make a small example. Again, let's say this is the base constraint. So now let's assume we divide by 2. We get this constraint. Now, let's say we do multiplication by this rule, which is 1 divided by 4. We get this one. But it's important that we have this plus epsilon, so it actually rounds up still to the corresponding upper integer. Yeah? So very trivial rule and is pretty bad. So the current division cuts that we use them are sort of suboptimal. And of course, this epsilon doesn't exist in exact integer arithmetic, but we can simulate them by certain large integers. Yeah? So we need to simulate this plus epsilon by large integer numbers. Yeah? But we can do everything by integer addition, multiplication, and division. Yeah? Okay. First, so I think this should be implemented. So I also dealt a little bit with multipliers for mixed integer rounding cuts. So there it's not that easy. So it's not easy to classify the optimal multipliers for mixed integer rounding cuts. Of course, we know that linear dominates the quadrigonoid cuts for every multiplier. But Bool seems to use also in that heuristic that they divide the whole near cut by several multipliers that look like this. And this is according to a paper that was written also a long time ago by Marchand and Wolsey. But we can actually construct also examples where these multipliers are not among the optimal ones. So this is also not a suboptimal, but I also didn't find any results that can characterize the optimal multipliers for near cut. But my gut feeling is also that the ones that were good for quadragomoric cuts, that means with this plus epsilon lifting up, rounding up, that these also often work very well for instance, rounding cuts by the sort of the same argument. Here you can, on this graph, you can see a little bit how one particular coefficient in the cutting plane evolves for different multipliers of this mu. And the red line is the quadragomoric cut. You see this like always piecewise linear, then it rounds up something a little bit. But the shape of the near coefficients, they look much more complicated, right? Sometimes it goes up, sometimes it goes down. And in order to really get the characterization of where the optimal multipliers are is, not that easy. But just wanted to stress that there's still some research to be done on how these optimal multipliers for near cuts look like. Okay. So, for conclusion, multipliers of the form can be strictly weaker than more general multipliers. Can use this without loss of generality and have no overhead. And my actual question would be, do cuts of the form 1 divided by d actually simulate more general cuts? I also didn't find any result on that, because I mean, it was also question whether we use maybe the cutting plane proof system properly or division as part of the cutting plane proof. And the same holds for mir. The question would be, why do we use such a restricted form division in general? Okay. Another idea that I think you were working in parallel on something very similar is like how to do weakening in a conflict constraint or in a propagating constraint. And I call this sequential weakening with improved rounding. So that means instead of so you take the constraint and there are multiple candidates on which you can perform weakening. And the idea is to define a weakening sequence analogously to a lifting sequence, and you just step by step look at literals in the sequence and you weaken them to a multiple of the coefficient of the equiliteral. And this yields a simple method. You just have like an overhead of O of n for the lifting sequence. And it includes also the original one, because in the end you will weaken or you iterate over all the possible weakening candidates. You can possibly partially weaken. So just to give an example why this can be useful, let's assume another example. This, and this is the propagating literal. So when we apply a partial weakening now, we would again weaken this completely away and this to a multiple of 4. So we have this constraint. Then assume we do round to 1 division by 4, which we would result in this constraint. Now assume we do RTO star, which is this improved rounding by this factor. We already get the stronger constraint, which we save, where we save 1 coefficient here in L3. Now let's assume we do partial weakening, where we only focus on weakening L5 to a partial multiple, to a multiple of the weakening constraint first. That means we would weaken this down and immediately then do this optimal rounding by 1 divided by 7, because 10 minus 3, we will weaken this away, and then multiply by this one, we even get a stronger constraint. Yeah? We can just run this as an outer loop on all the possible weakening candidates as a weakening sequence. We will also include the method that we had before, and actually may get stronger constraint. So this is an example where you just have the whole chain where it really. Okay. So, and yeah, you can prove basically this, that the improved rounding procedure better than the original, and if you include sequential weakening, because just an O of n loop on top of it, then it's also better. And the near version is always strictly better than its counterpart. Okay, so now maybe I still want to talk about like some cut selection measures, because in conflict analysis, we very often have the problem that we can generate a lot of different cutting planes and we do not know which one we should actually take or which one is good for our problem. And yeah, for example, we can look at these two constraints, and in principle, it's not really clear which one is better than the other, just by looking at it, right? So which cut is better, C1 or C2? So yeah, I don't know. So probably we need to have some measure, quality measure on to address which cut is the better one. And in the MIP community, there's also an interesting paper about this. Several metrics have been developed to measure this quality. And one of these measures is this efficiency measure, which computes, okay, this is not a literal form now, but it's more in vector variable form, where you according to some point x, feasible point x, could be in the mid world, this is normally your LP solution. You compute the slack and divide it by the norm of the vector. So this basically means it's the relative slack of. You can also interpret it like you have your point of your polytope, and then you look at the cutting plane and you just look at the closest distance between the cutting plane and the point. In principle, you want to probably maximize the efficiency, but as it's stated, you want to minimize the efficacy. And yeah, you want to select according to this measure. For example. This is one of the standard measures. And yeah, coming back to another example, if you compare these two constraints, and let's assume you have an LP solution that is here, or maybe some partial pseudo-Boolean solution that can be indicated like this, then you just evaluate this and you have a measure, and here in that case you would think like, oh, even the clause is actually better than this more complex. So this is one way of doing it. Because according to this solution, the causal cut is further away from the actual LP, so it cuts off more from the polytope. Okay, then there's another measure which they call directed cutoff distance. This actually sets, for example, the LP point that we have in relation to another point, and looks, okay, now I travel from this point to the other point, and I count, okay, when does it hit the cutting plane in the middle? We can actually interpret like this. So here's the one point, here's another reference point. The question is like, okay, which point do I hit this cutting plane? So this is what this measure is saying. Right? And the question here was, which reference point should we use for our LP solution to measure the distance? The good idea was in the paper that dominated all the other approaches was to use the analytic center. The interpretation of this is that cuts should always point in a certain way towards the inside of the polytope. Because you always want to cut away something from the outside of the polytopes, and they should always be in a certain way in a right angle towards the center of the polytope. And in PV solving, we normally will not have an LP solution, but we can simulate an LP solution by just assuming maybe values for those values that have not been assigned yet. So the idea would be here to assume that the LP solution is equal to what we have assigned on the trail, and for those values that we have not assigned anything on the trail yet, we could just assume one in order to make it, for example, maximally feasible, the constraint, which we also do during slack computation. Actually, we always have like optimistic assumptions in our subroutines, and yeah, this is, for example, something that we could assume, and this is I think a good idea that we will implement for sure next. And I think having a good measure of this, and of course we need to check what the performance is, but I think in general, having any of these measures will help probably a lot in order to evaluate the quality performance of such. Any questions for this part?
Can you say anything about how much of this you've tried out in your solver?
Actually, this is just idea gathering. I have not implemented, but I will implement this now soon for sure. And I think because, if you read this paper, this analytic center was very successful, and to the best of my knowledge, it's by now implemented in Gurobi. Yeah? And this turned out to dominate all the other approaches, and I think this approach works very well. Because it has also this nice integration. Yeah, you always want to cut something through the inside of the polytope. Yeah? And because sometimes the LP solution or any other reference solution that you may take here could be somewhere else, but it's maybe not, because this cutting always needs to be feasible, and there might always be some integer point in the way that you cannot cut more. So a good measure is always like, okay, take your LP solution, and then look into the inside of the polytope, and then maybe try to cut away something from there. So this seems to be a good approach. So, and I do not see any point why this should not be good also for pseudo-Boolean solving as a measure.
And the things you talked about earlier, like clique detection and these kind of, with MIP solvers would normally do this?
They do it, I think, also in the pre-processing for sure. Yeah, they do it. It's a standard techniques actually. They have click tables where they store many clicks, and they do it for sure in pre-processing. If during the solving process they do get additional click cuts, I'm not super sure. But I think for sure in pre-processing. Okay, so with the next part, then I would maybe wait for.
Maybe this is a good, yeah, so it's a good place to take a break. And also, if there are other questions. So what's the reference for this? That's the click coloring formula. I guess you need to figure out that okay, so if you would want to argue that maybe even, I don't know, like, I don't know if you need extended Frege or if Frege is enough to do some kind of symmetry argument. Again? This is 0 Frege is over. So there's this.
What's this result? Exact result there?
So I think that there are the first formula, or I think it's the first, or at least one of the first formulas that are known to be hard for cutting planes, is the so-called clique coloring formula. You write down a formula saying that I have a graph on n vertices, and then you say something like it has. So a graph on n vertices, then you pick some m, which is like, say, square root n or something like this. And then you write down that this graph has a clique of size m, but it's also m minus 1 color. And this is obviously impossible, and so it should be possible to you can prove that this is contradictory, but this is hard for cutting planes. If you pick this clique size m to scale polynomially with the number of vertices n, then you get an exponential. Now, a proof system that is, I don't know how bounded that triggered that. I guess if you have some kind of symmetry reasoning, then now you can obviously just say that, well, without loss of generality, if you say you have a clique on m vertices, well, without loss of generality, these are the m first ones. Okay. Now you just, let's focus on coloring the m first vertices. Then you realize, but I can't do this. There's a clique there. But I assume if you have a bounded that Frege upper bound, it might be doing something different.
There exists standard Frege proof, or
So even no, apparently like much weaker system. You don't need to go to extended resolution, even much earlier. So there's like if you have resolution without the extension rule, but you extend resolution so that it's not operating with clauses, but it's operating like with and or formulas. You can still kind of if I just have sort of and or not formulas, you can still define resolution where you say like if I have a formula f or g and another formula not g or h, then I can quote unquote resolve to get f or h. Okay, so this now defines a resolution-like proof system, but over like nested formulas. Okay, and without any restriction on the nesting depth, this is modulo that I'm describing this in a very hazy way. This is the so-called Frege proof system without extension rule. Now, if you want to make this weaker, you can say, yeah, but your formulas can only have limited nesting depth. Then you get bounded depth Frege. And bounded depth Frege, we don't have lower bounds for Frege, but we do have lower bound for bounded depth Frege. For instance, the pigeonhole principle is still hard for bounded depth Frege. But only the precise pigeonhole principle that says that n+1 pigeons fit into n holes. Like if you have a more approximative counting pigeonhole principle that says, I believe 2n pigeons fit into n holes, then this is still hard for resolution to say that this doesn't work, but already bounded that Frege says it can sort of count approximately and say, no, 2n is too much. You only have n holes. And I guess that kind of approximate something like no. The impetus error that would have come before even. Maybe we just have to take, but it's known. It's and I think it's yes. That's the reason. Any other questions or comments? Let's take a break. Oh, actually, let's thank our speaker. Sorry. All right.
So we are back after the break, and we're going now into even more technical details about pseudo-Boolean optimization. So Alex, please.
Yeah.
Or is all yours?
Thank you, and welcome back to the second part. Now we'll talk more about pseudo-Boolean optimization, and in the combination with duality, in particular p-duality. And I want to draw a connection what kind of methods we actually use already in pseudo-Boolean optimization and how they can be interpreted in the mid world, and in particular also in the LP world, where we can use duality in order to improve certain things in pseudo-Boolean. So let me first revise which methods we actually know in pseudo-Boolean optimization, or first, what is the pseudo-Boolean optimization problem? So I write it here in more mid form, where we have consider again Boolean variables. We have cost function C that we try to minimize. We have a constraint matrix that multiply with the Boolean vector. This must satisfy some linear constraint according to our right-hand side. So this is in principle Boolean optimization, right? Nothing new. The PB version would be to minimize. You can also write it again into literal form, and we seek to minimize a linear cost function of some literals according to a given set of PB constraints. And again, the literal representation is nothing more than just expansion of the variable space according to a linear transformation. So that's why we can always interpret it in an equivalent way. Okay, so I will just quickly review the methods that we know for pseudo-Boolean optimization. So the most simple one is linear search, so where we perform a series of subcalls of the PB solver according to an upper bound on the objective value. So this is more the type of primal approach where we find a feasible solution and then try to optimize from the primal solution on down to the optimum. And the algorithm works as follows. So we initialize initial solution. So we have no initial solution yet, so it's the empty set. Then we solve the PB problem P according to the original problem that we have. If this PB problem is answered, then we return the last solution found. But right now we don't have any yet. So otherwise, we set this to the current sub-solution. We derive an upper bound according to the current cost of the solution. And then we add like an improving constraint that sets the cost to the upper bound -1 in order to be strictly improving in the objective function. And then we repeat. So this is very straightforward. Pros of this approach is, of course, okay, we can reuse conflicts that we have generated along the way. So we don't have to throw away everything, but we can actually reuse conflicts that we generated in earlier iterations for higher upper bounds and reuse them in later iterations. And we can also use heuristics for warm starts in order to improve the upper bound already by default and just warm start the solution and then continue the search from an already good solution. Once is, of course, when this approach is very inefficient when the cost range. Okay, so this is then we have the implicit hitting set approach. Here again, given a Boolean optimization problem. The idea here is in principle to define an a priori relaxation P prime that may consider a subset of the constraint, or maybe even not any constraint at all in our model. It can be even an anti-optimization problem that just has the cost function. And in the beginning, we optimize the relaxation and we get some solution. We set a set of assumptions according to that solution that are sort of overly optimal, and we can fix this overly optimal solution and try to give it to our PB SAT server and ask, okay, is the solution feasible? Most likely it will not be feasible, so we can derive core constraints out of this. And or we cannot derive a core constraint, then we actually know that we are optimal because we were overly feasible. But if this is still feasible, the core solution, then we know that we're optimal. Yeah. On the other hand, we derive a core constraint, and this core conflict constraint we can then add to the relaxation and repeat the procedure because we know that in our relaxation that we solve the same solution will not be taken because this is excluded by the core constraint. And then we can repeat the procedure and solve it until the problem is solved. This is, in contrast to the linear approach, this is actually a more dual approach because we always find like overly optimal solutions and always increase the lower bound or come, so to say, from the lower bound to the optimum closer, while the linear approach goes from the prime solution down to the optimum. Yeah? And yeah, similar. Okay, the pros of this approach that problem can be solved fast when we can really extract essential cores from our PB solver that are very good in order to solve this problem, and maybe we just need a couple of core constraints from our basic model, and yeah, so maybe we have like a million constraints in our original model, but maybe you just need to add like 10 in order to get to the optimum. Yeah, and this is very fast because then we don't need to have like an overly efficient optimization method in order to solve it, but we can, for example, also very often an IP solver is used, but we can then solve this problem actually very fast in a small number of iterations. Yeah, on the negative side, we need, of course, an efficient method to solve P prime. We could use a PB solver. That's a little bit like a chicken and the egg problem that we solve an optimization problem with a method that we actually use in itself. So normally you would probably use an IP solver or an external method, or for example, also linear search you could use if the problem is small enough to solve. But another on the negative side is that we may recreate much of the original problem. So when we have an overly optimal solution X prime, and most likely it will not be feasible. Yeah? But then we derive a core constraint that could actually be just a constraint of the original model and then add it to the relaxation. So it could actually happen that we just recreate the original model into P prime and then actually tend to solve actually the original model just when the core constraints are not very expressive. So that means the core constraint that we derive could always be an original constraint of the model, which would not be very efficient. Yeah? So, but this in principle can happen. So, and in that case, the method may not be as.
If we're trying to make connections as we are between MIP and pseudo-Boolean solving, it might also, I mean, a MIP person might also refer to this whole thing at logic-based Bender's decomposition, where the master variables are like the objective.
You can definitely absolutely refer to it. There's also more MIP perspective that is a paper of if I'm not mistaken. They also tried an approach of Bender's decomposition, combinatorial Bender's decomposition. So it's very, very related and very similar. I didn't want to get too much into this comparison, but I want to compare more to the MIP world the next approach, which is core-guided search, which is a maybe even more prominent example on how to solve right now pseudo-Boolean problems. So let's just assume our objective function is given in this sort of literal form, and we can assume that the coefficients of our cost function are positive, without loss of that. So then the algorithm works as follows, also similar actually to the previous approach. So we have a set of assumptions, and the set of assumptions are that collect all the literals that we have that have positive cost coefficient, and then we solve E with the set of fixed assumptions, but contrary to it, so the assumptions are set to false, and then we plug it into our PB solver, and then we ask, okay, is this model feasible when we set all the literals that have a positive cost? If we set them to false, plug it into my PB solver and ask, is this feasible? Because we again make like over-optimistic assumptions. Everything that has positive cost, we set it to no, we don't want to increase it, so we set it to 0. Ask if this is feasible, and assume this is feasible. Then I know that I'm optimal because my cost is just optimal. I can set everything to 0. This must be optimal. Otherwise, I can extract again a core constraint, and I can perform an update. And how this is done in the original paper is that the original core constraint, which might be a general pseudo-Boolean constraint, is converted into a cardinality constraint of this form. And then we perform an update rule. First, we add this to our original problem, introducing new slack variables because we need to have an exact reformulation of our objective function. So we need to have this equality. For this, we introduce slack variables because it's just an inequality. And according to this, we update the objective function by introducing this term, which is just 0. We just reshift the terms here, and we determine this alpha by the minimum of the cost of all the elements that are included in the cardinality constraint. It's derived from the core. Right? And in particular, when we choose alpha like this, there will be one term removed from the objective, and also the lower bound improves by alpha times k. So it's strictly positive. That means we really improve the lower bound by 1. So it's a finite method, and eventually it will converge to the optimal solution. Okay. So this is a sound and exact and complete method of So yeah, as I said, we remove at least one literal from the objective in each iteration, and the lower bound is certain. So at some point we have to just arrive at the optimal. Okay, actually I wanted to end here, but I will continue here. So now, I think an interesting term is maybe how can we generalize this core-guided search? A little bit of Because right now it seems like, okay, we have some ideas that we carried over from SAT or MaxSAT, and we try to carry them over to pseudo-Boolean solving. But what is actually really a broader interpretation of this in terms maybe of mixed integer programming or linear programming would be interesting. So, and the first approach is how we generalize core-guided search. So it's also based on a paper that is not published yet, but working on this. But I want to present the ideas here already. So let's just assume we have a cardinality core constraint, right? So, and the update rule for the objective function basically looks like this. So we up phi is the objective function in literal form. If we update this to original cost function plus this alpha times this term that is supposed to be 0 because that's how we just defined it, introducing the slack variable. Yeah? Here we use in particular binarized slack variables that represent actually an integer slack variable, but we can just represent it as a sum of. And we choose this alpha as this expression where this should be an S prime here actually, and S prime is again it's a subset of the assumptions that I've done. Okay, and in particular, all the literals that have a cost coefficient that is equal to alpha will be removed from the objective. So at least one is removed from the objective. Of course, this is how it's done right now, but maybe we can generalize this to and not make this conversion to cardinality constraint, but maybe just derive the general. Okay, so assume a general core constraint that just looks like this. So can we generalize that? So what we will have is basically again this alpha, and we have again the slack variables. Everything is integer, so we can just introduce again integer slack variables. But we just have these coefficients here, which is new, that we didn't have in the cardinality constraint. So now the question is like which alpha to choose in this case. Okay? So actually, you think about a bit about it, and then you actually arrive at the term. So the answer is we can, according to the same logic that we had before, we just choose because we always want to at least one will be deleted from the objective function, but also we don't want to overshoot because we want the coefficient still to be positive. Yeah? So that means we just by looking at it, we just define the alpha as this fraction. Yeah? A little bit provocatively, I already write here AI greater to 0 because this is an expression that many mid people would know from somewhere. Yeah. So we can set this alpha to this expression, and we know. The question is like, what is this here? So, does anyone know or has seen this before at some point in operations research lectures? Or I mean, when I was dealing with this and I was looking at this, okay, this I know what this is. So this like this.
Oh, it's the thing in the simplex tableau, the ratio test.
Exactly. That's right. So this is actually nothing else than the ratio test of the dual simplex. So, and of course the AIs are always 0 in our representation, but in a normal LP representation, this is normally not the case. So you would have to enforce this condition. Yeah? But this is actually exactly the ratio test of the dual simplex. So that means this multiplier alpha can just be interpreted as a dual value of the new core constraint that is added to the problem. Yeah? Okay, so what can we infer from this? Can we do something with this? Can we have like a broader interpretation of these dual values here? It's interesting somehow. And yeah, I mean, maybe let's have a repetition of P a little bit in a nutshell. So okay, we can state a primal LP that is this, right? We have cost function, we have range matrix, and we have non-negativity condition. For every primal, we can state a dual LP that just basically converted from that. So where we max the right-hand side times the dual value. And here we have the transpose constraint matrix times the dual vector must be smaller equal to P, and also non-negativity conditions for dual variable. Of course, we know that the solution spaces of both of them are integral. And we can also always convert any LP into standard form where equality holds. We will use this later still, but I just want to mention it that we can always convert it to standard form so that we have more variables than constraints. Okay. Then let's repeat what the basis is. The basis is defined as a set. Okay, we assume that the number we have much more variables than constraints, and the basis is a set of n. That means the number of constraints linearly independent columns. so that we can define from a given basis B a basic feasible solution, because this is invertible when they're linearly independent, right? So that we can find this basic feasible solution as x equal to the inverted basis times the right-hand side. So basically, b times x must be equal to b. Yeah? This is how a basic feasible solution. And for example, every corner in the polyhedron, every LP solution or optimal LP solution is a basic feasible solution. So there exists a basis that defines this solution. Yeah? Because you can interpret it as an intersection of cutting planes, or in a higher variable space, like the solution of the set of an independent column. Okay, then there is, we know that weak duality holds, which basically means if we have any dual vector for the dual, with any vector for the primal, we know that the solution value of the dual always a lower underestimator of the solution of weak duality. Of course, and there also strong duality. That means when we solve both of them to optimality, we know that the solution value coincides. And also known, we have algorithms to solve this with Fourier point, primal and dual simplex. And of course, the simplex algorithm works by basis exchanges. So we start with a feasible basis, and we find columns that have negative reduced cost, and then we let it enter the basis and replace it by another column that was in the basis. So we basically made a lot of basis exchanges until we arrive to the optimum. This is how the simple. Until all the reduced costs are not negative. Okay, like how does this simplex interpretation look like in a Tableau form? Let's look at it. So probably many of you have seen this kind of representation already. Let's assume we have an optimal basis, right? This is like our constraint matrix that is defined by an optimal basis AB, which is a selection of independent linear columns. And AN are the ones that are not in the basis, that are, so we assume always that we have more variables than constraints. So this has this rectangular shape. Then we have the cost of the basis columns or basic variables. We have the cost of the non-basic variables at the right-hand side. And we have an optimal solution, x star, which is greater or equal to 0. And we have here the non-basic variables that are always 0. So then we can define the reduced cost. So let's have a simple reminder. What are the reduced costs? Reduced costs are the CB minus the dual values, or minus the basis matrix transposed times the dual vector. And so you can basically see this as a little bit shifted by 90 degrees, and you just subtract this reduced cost. Here for the non-basic variables, you can do the same. And we know that in an optimal basic feasible solution, that the reduced cost of the non-basic variables are greater or equal to 0, and the reduced cost of the basic variables are equal to 0. So, and we also know that the complementary slackness condition holds for involvement. So, okay, where do I want to go with this? So, this looks a little bit similar to what we do in core-guided search. I mean, whenever we update the objective function, we actually make kind of reduced cost update, right? So we reformulate the objective, and these can be interpreted as the new coefficients can be interpreted as reduced cost. And whenever we introduce or find a new core constraint and compute a dual value to this, then we just set a dual value for it, right? And in principle, pretty much very similar or the same what we do. So we can, so basically what we do in an update step of core-guided search is that one variable gets deleted from the objective function, which basically means, okay, this variable actually enters the basis because now it has a reduced cost coefficient of 0, right? There might be still other ones that have like a positive cost or a negative cost, let's say in this way, and those we want to fix actually, especially those that have a positive cost coefficient. these are actually the ones that we want to fix to 0. But here also in the linear field, the non-basic variables, they also have a solution value of 0. We actually kind of like do very similar things, right? So whenever the reduced cost is positive, we want to fix it to something that is 0. And whenever they have reduced cost of 0, we leave it free. So these are the free variables. And in the optimal LP solution, whenever I have a positive final value, then I also know that the reduced cost must be 0 of this book. So this is pretty much similar and the same what we're doing. Now I actually want to say what we can do. For example, I mean, there exists a very similar method in MIP that's called Komori's cutting plane method, which is also an exact method to solve mixed integer programs. And it works actually exactly like this. We solve an optimal LP, and we just look at the current primal solution, optimal primal solution of the LP, and we can derive the cutting plane from this solution, which operates on the remaining fractional parts, but we can derive a cutting plane from the optimal tableau that is violating all the non-basic variables. That means basically for those variables that we have, like, so the set n can be always interpreted as the set of our assumptions. Yeah, so it generates a violated cutting plane for those elements that we have set to 0 in our assumption set. Yeah? And here we just look at the LP tableau, and in the core-guided approach, we fix them by over-optimal assumptions, so to say. We don't solve an LP, but we fix them by over-optimistic assumptions according to the reduced cost, while the LP has an exact representation of the reduced cost in an LP set. And we can derive a Gomori fractional cut, which I already write here as a C core. This is kindly interpreted as the Gomori fractional cut can be actually interpreted as a core constraint that works on the set n, which is similar to the set of assumptions that we do, and derives a violated cut here. And what it also does, the cutting plane method of Gomori, is to add a constraint with slack variables that is then added to the model. This is exactly the same what we do in core guided search. Yeah? What Gomori's method is doing in the next step is performs a dual simplex step to compute the corresponding dual value to let this, because we added a new variable and a new constraint to add it to the basis. So that the reduced cost of this element becomes 0. This is also exactly what we do in core-guided search. So we also find one element that gets a reduced cost of 0 then after the pivot step or the update rule in the core-guided step. So, and we expand the basis by it. So a lot of similarities. So maybe I will try to summarize and put them exactly next to each other. Core-guided search and Gomori's cutting planes. So here in the core-guided search, we fix optimal assumptions to 0 for all the literals that have positive reduced cost. Here we kind of like in the LP method, I mean, the LP computes the solution already, but we can also kind of interpret it a little bit in a way that we fix the optimal solution to 0 for all the non-basis elements. Yeah? Because this is just the definition. All non-basis elements have like the p-value of 0. Then we compute in a core-guided search, we compute a core constraint that is violating on the set n of assumptions. While here in Gomori's cutting plane method, we compute a Gomori fractional cut on the non-basis variables that again correspond to the set of assumptions. And but we just derive this cut from the optimal tableau. While here in core-guided search, we derive this core constraint from conflict analysis, not from the optimal tableau. So then we add this constraint to the model with the binarized version of slack variable, but in principle we have a continuous slack variable if you want, so we just binarize it in order to make it representable, and because of all of our data is sort of integer, so we just binarize it here in our PB setting because we need to deal with Boolean variables. But in the normal cutting plane method, we just add like a continuous slack variable. We can operate on that further, right? And yeah, the last step is basically completely equivalent. Yeah? So we just perform a dual simplex step on the cut that we have introduced, and this is more or less completely equivalent what we do. We increase the lower bound and we update the reduced bound. So there's a strong similarity here between these two methods, which I just want to address here. But actually, we want to use this method somehow. Maybe we can use this type of interpretation somehow for something in Boolean solving. Okay, again, let me conclude here with this. Core-guided search basically corresponds exactly to the Gomori cutting plane method, only that we do not derive the cuts from the optimal LP tableau. We derive them by optimal assumptions according to conflict analysis. So eventually we can actually derive stronger cuts, or maybe not. I mean, because actually LP cuts can sometimes be like very strong that maybe pseudo-Boolean solvers cannot derive, but also because we use like all these strengthening techniques along the way, maybe also the pseudo-Boolean cuts could be like stronger than what the LP can derive. So it would be interesting to discover a question. And also what is interesting, because we discretize the slack variables, we can actually, in pseudo-Boolean optimization, we can reason over these like over these discrete slack variables and maybe build higher level of logic on top of each other, and maybe because it's a good extension rule. And the LP, for example, does not do it. Can of course derive and include the slack variables in a future conflict still, but it will still deal with it as a continuous variable, and it's not clear like what it does with it. But here we can use it really as binary facts and maybe build stronger models on top of each other. So this is kind of the difference between these two methods. I just wanted to stress that the core-guided search, this is kind of known in the IP world. And also Gomori's cutting plane method is a long method and has also like its pros and also its drawbacks. Okay, then which open questions, which cuts are stronger, and binary slack variables really encode higher level features of the problem. So this would be interesting questions to address. Okay, so now to conclude.
Are you aware, just to say, so I think this sounds somewhat similar in spirit to a line of research that George Katsirelos had. Have you seen his papers?
I read this a little bit, but I did not see him mention this method particular. But what he does is also somehow combining this in a way with linear programming. But yes. I think he still does it a little bit differently. Probably. But I cannot. Also, notation-wise, I think it's not sticking so much to the standard notation of the IP world. So I have to dig deeper into it. Okay, so now the next point that I wanted to address will be even more confusing probably in the LP world, because I mean, of course, the simplex is not the only thing how we can address LP solving, and we can also have other approaches, and these other approaches can also maybe be used in a different context. Also, let's just start. Because actually I wanted to introduce an example which can also be confusing, how we can actually improve eventually core-guided search. So let's just look at this object. Assume we learn this core constraint, right? So nothing special. So by the current update rule, we would just perform this update here. So our just update it to standard cost function that is above here, plus some lambda dual value, constraint multiplier times this term, introduce the slack variable additionally, which boils down, this will come out in the end, and we have a lower bound here of 2, right? Or the given lambda equal to 1, which is computed according to our rule. So, surprise, surprise. So we can choose a different multiplier, lambda equal to 5. So, and we can just obtain a larger lower bound. So now, we have a lower bound of 6 versus a lower bound of 2. Now the question what happens here? What is the interpretation of the small? So you probably have observed something similar already. Yes. So okay. So now, of course, the question is like, can we interpret this somehow in the LP setting? Oh, what is this? This magic. So why should we do it? Why should we do it? Or can we generalize this instead? So Okay, yeah. So the lower bound can increase further because the signs and the objectives can obviously switch from positive to negative. And because of this, we can now we can work out the math a little bit. So we want to find the maximum lower bound update, which is this. So assume we have given an objective to minimize this term and the core constraint like this. And so then we can define actually the optimal multiplier that maximizes the lower bound is given by this lambda, which is fraction of certain index p, where p is equal to, which is the first index that when we sum up the coefficients, so in increasing order of ratios so that the constraint is satisfied.
This is now we're doing this for general pseudo-Boolean constraints.
Yes.
Mm-hmm.
Absolutely.
Mm-hmm.
So this is the proposition. You can prove it if you want. So more sophisticated session now. So it's actually not super hard to prove. So by the update rule, we have this term, right? So this is just the update rule. So let's just assume that when we subtract this term, that this will exceed the cost of some literal that we have in the function, then this term is okay. Let's assume this is bigger than this one. Then this term is subtracted additionally from the lower bound. Okay? Yeah, because we can make the math here. And because for the coefficient, then it holds ci minus this, go to this. This we can then just derive as make it negative as a literal, and then have okay, this is simple. We can therefore represent the lower bound increase by this term, which is just lambda times b minus for all the ones where this is bigger than this, and then this term just accumulated. And rewrite this as this term, which is now depending on lambda. And yeah, we can look at this function f of lambda. This is like piecewise linear and concave, and so where the slope starts at b, and then it successively decreases the slope. Okay, you're nodding, so maybe you have done something similar already. So this looks like this, and here on these like iteration points, it's always where these fractions are, where the new lambda basically enters the computation and where the slope is. So the maximum is exactly given when slope changes from positive to negative. This can only be according to this formula here when this term exceeds this b, which is basically this term, which basically is the first index where this. Okay. It's a very simple. So, and this here is quite interesting here, this graphic. I will come back to this, like, what is this here? So, okay, so as a special case of this new update rule, for example, if the core constraint is still a cardinality, could happen, we could get a cardinality constraint, then the lower bound now increases by exactly the sum of the k minimal element. So the sum of the k elements which have the minimal reduced cost. So it's kind of like best portable in the sense that we can increase the lower bound by that amount because we can just sort them by the reduced amount. And if we know that at least k of them must be satisfied, then we can just sum up these terms about the reduced cost. So it seems like optimal in a sense. Okay, we can improve the lower bound by that amount. And this is also cool because, I mean, we still remove exactly one literal from the objective. So still sort of like simplex step. It's actually not a simplex step, but we'll come to this later. But it's still we still remove one literal from the objective, so it still kind of like reduces the cost. Nice. And we can use this rule actually directly as a replacement in call-guided search. Why not? Yeah. So if the objective function still increases, we can just directly use it and do something. But again, what is the proper interpretation of this? I mean, what we want inside, right? So there I come to Lagrangian relaxation, so which is a very common concept in mixed integer programming. We can again look at the linear program that looks like this. And for a given dual vector, we can consider the Lagrange function. This is basically where we minimize the cost function, but now we add penalties to the constraints when they are not satisfied. And then we want to increase the cost function. So it's called the Lagrange function. And we can just shift these terms around, and we see that here we get exactly the reduced cost for the term. Here's this x, and this is a constant term. This is not necessarily the lower bound. I mean, it's in certain cases it's the lower. So, and what we can see here is actually, if we want to solve this to optimality, right? We see it's linear function in x. We can just solve for the optimal x, which is just given by, okay, we set x by 1 if the reduced cost is negative, or otherwise we can just set 0. Actually, when it's equal to 0, we can choose anything. Yeah? That's the question what we choose there. But when it's strictly positive, we have to choose it. So this is exactly the same also what we do in code. So again, a lot of similarity. But the x that we compute here may, of course, not be feasible because we do not really respect that it needs to be feasible. We just analyze it when it's infeasible in some constraint. So the x may not be feasible, but for this reason, we can increase the penalties by in a new function, which then called the Lagrangian dual, where we additionally maximize over. What we can do here, okay, so the relationship is that the Lagrangian function is the lower bound on the optimum here, but we know, and it's a theorem, that this Lagrangian dual is the maximum over this is exactly equal to the optimal value of the relaxation. So in principle, what we compute here is the optimal dual value of the optimal dual vector. We can solve it by a subgradient method, which is actually decently fast. So if you implement it. Okay, but what can we learn from this? So we've seen this picture here before already, like this envelope here, this lower one, in the proof. And you can, by solving the Lagrangian dual, you can see that this Lagrangian dual, just a collection here of piecewise linear parts, and we want to compute like this the maximum value of this lower envelope here. This we can do by subgradient optimization. We can just compute always the gradient here, which turns out to be the slack in each object, and then move in the right direction. And under certain mild assumptions on the step size of the functions, we can get to the optimum. Okay, this is the subgradient method. I will not get into detail here much. But another observation is that actually many of the current local search heuristics for pseudo-Boolean optimization are based on very similar techniques of duality. Actually, they call it always penalty weights for the constraints and so on, and they use slightly different objective terms, but in principle, this is all based on the same dual idea, where we have penalties or dual values on the constraints. Then we flip them according to the reduced cost that we compute. And our LazyPB also uses as a primary heuristic also method that's based on subgradient. You have to introduce a few other terms in order to make it more feasible and so on, and also add a few adaptive terms to make it actually work. But in principle, it's a dual idea. Okay, so this is just to compare again the minimum reduced cost update that we had before in standard core-guided search. So this is like the generalized approach that we introduced. So this is like the new lower bound update with a maximum lower bound. So what is the difference between these two approaches? Actually, essentially. So essentially, in the first version, like the generalized version of what we have right now, so we always stay dual feasible in each dual simplex step that we do. Yeah? And the lower bound can be then computed by that. This is a vague guess. I implemented one of these methods, so this is also like a vague statement of first computational results, but of course you have to verify the paper properly. But with this approach, you have potentially more iterations and the sub-problems from my first computation seem a little bit easier to solve. Because it feels like whenever you have like a simplex also, you start at some iteration, there's a natural direction, the natural problem to solve to move to the next problem, to the next sub-solution or sub-problem to solve. But if you have this lower bound max update, you make much bigger steps in the lower bound. It may distort a little bit the reduced cost vector and may a little bit get tricky to extract cost because the combinatorial problems get a little bit more complicated, like much faster. So there's still a little bit of research to be done, but yeah, these were kind of like the first observations that the reduced cost when you use like bigger step sizes, so to say, in the lower bound, then the reduced cost gets a little bit distorted, and the solver doesn't really know like or the problems get harder much faster, because you also approach the lower bound much faster. The more you come closer to the optimum, the harder the problem normally gets. And this kind of behavior you can also see there. And it's still like a little bit of a problem, which type of optimal modifiers you should use. Should you use minimum, or when you should use the reduced cost update? Can it be better? Or should you always aim for maximum low, to maximize low? Also not, of course, and both approaches coincide when okay, now I developed an algorithm out of this. Yeah. So, okay, we have again a problem. And the basic idea was to compute an initial dual vector to start the search with, by a subgradient method. Actually, an integer subgradient method, because I mean, right now the implementation still has floating point, but it's maybe not such a good idea because of like obvious reasons of the computability. Even though you could make it work, but it's a different question. But in principle, the idea is that you compute an initial dual vector who won't start the search, so you get a good lower bound already, and you get a reduced cost vector that aims already in the right direction where you should search for cost. And then the main loop is basically straightforward. You compute a reduced cost. You again make assumptions according to the reduced cost. You solve it with the fixed assumptions, derive a core constraint eventually, and then you just add it according to the new update rule, or maybe the old one. It still needs to be tested which one is better, but you can then just apply the new update rule and perform dual simplex step. This would be like I call it dual value core generation, because you immediately make a dual, compute a dual vector, and you also compute like better dual vectors along the way.
Do you think about the coefficients of the slack variables here? Because now you can suppose you have fairly large coefficients AI, then like having a slack variable, like unit slack variables, is not obviously great.
I mean, for unit slack variables.
With coefficient 1, because you know, like you won't, the most values you cannot hit. So somehow you'd like to, in a optimal world, you'd like to introduce slack variables only corresponding to values that this linear form could actually hit.
Yeah, it's not optimal, but I didn't think about it. Yeah, I mean, eventually they have to cancel out the closer we get. I mean, also you don't create all of them.
No. Yes.
So actually, I don't care if some of them has small value. I mean, of course,
you might care if you introduce lots and lots and lots of them. That could be quite potential. I mean, the reason why we're being lazy in the first place is because if we were not lazy, then we'd take a major hit in performance.
I mean, this can definitely happen. Also, of course, if you have this more linear expression here, I mean, this becomes much more, so the number of variables here scales also with the coefficients, which can be much worse, of course.
Yes.
Yeah? So this is that already. So that's why this is the more general approach, and then of course you have to look again how to make it feasible in practice. Right? Eventually, you still want to actually do cardinality conversion here to make it like feasible. Even though I mean you have to see, I have to really test it on hard data. So
it's not clear if you want to
because-
convert to cardinalities or not. I mean, there's this Correo group in Helsinki has worked on trying to do core-guided search with core constraints that are not cardinality. But I don't remember exactly. I sort of did. Is there even a paper about this?
Yeah, the SPK2 paper by one of the main contributors to the constraint. Sorry, IHS. That's IHS.
That's IHS.
I don't know about core-guided.
Oh no, because IHS then you don't have a problem, but core-guided you. No, IHS you're not introducing anything. Core-guided, the whole question becomes how are you going?
I think they tried it out like in the form of this. Not outside.
I think there's like sometimes it works great, sometimes it doesn't work so great, and I think it's like it didn't work well enough to actually say like yes, this is what we're gonna do. Mm. So, you can just there are the general core constraints will be stronger than cardinality constraints. Yeah. On the other hand, as you say, like for cardinality constraints, it's kind of easy to see what your lambda should be, and it sort of
seems more bounded in the number of slack variables.
And the number of slack variables, then you know that you're going to need all of them, and you just introduce them lazily one by one, and it's like a nice world. But definitely, I think also, I don't know if the Demirovich's group in Delft played with this also. I mean, at least he said he was going to do it. But I don't know if they. I mean, this perspective on it, I have not seen before. Like taking a step back and putting on the right glasses and like, aren't we doing actually this? I think is very interesting and potentially quite helpful.
Also, I mean, what I wanted to actually also stress or indicate with this whole setting here somehow that duality plays an absolutely major role in mixed integer programming. I think also when we are thinking also about conflict analysis and stuff like this, that these dual vectors, they give us some sort of indication on how we combine stuff. Here we can also do it like in an initial approach already. We just compute some subgradient method, and we already have a much better idea how the reduced cost looks like. But it also gives us a direction where we should look for cores. Yeah? So it's basically we have so many reformulations for every dual vector basically, and we can already get to a very good point already without putting much effort in our PV solving approach. We just compute some good dual vector wherever it comes from. Yeah, then we can start already from there, search a good search, and this already this warm start in the duals already gives us a good warm start or a good starting point where we should look for cores, and of course the number of total iterations that we need should be much smaller, because in the best case we already we converge to the optimal LP lower bound. That means we can start from there on, and we reformulate the objective, and everything from there on is maybe just a few core iterations. So this is the basic idea. So also the whole setting, just maybe to also use duality within conflict analysis or inside of the solve. You just have this view, oh, there are actually dual vectors and we can combine stuff with each other, and this could be useful. It's very important. LP theory helps a lot to understand. Okay. Yeah, in practice, I mean, I actually implemented like a basic version of this already with a warm starting. So I also had some drawbacks, so it's not a fully finished method. So there's still a few problems that you need to deal with, because from my observations is that, I mean, first of all, we might need integer dual vectors. Not super necessary, because it just indicates like which assumptions we're going to take, and this can be just a heuristic in principle, so we don't need to be like super precise there. But actually, when we want to stress that the reduced cost is 0 somewhere, then you need to work with tolerances, which is not so much. Right? So maybe eventually you want to switch to integer dual value. But the caveat of this is that the lower bound can be much weaker than if you stick to integer value, because you just restrict the dual. Yeah. So open problems, can we handle so many slack variables, and yeah, which update rule actually works better, and yeah, which order of assumption literals should we take? I think there's also work done on this already, but still kind of like an open question. Yeah, first experiments. Okay, so when you do these dual warm starts, so you actually get much stronger initial lower bounds. It's to be expected, because you basically converge to something that's close to the LP optimum instead of like starting with 0. Yeah. So, but yeah, restricting to integer lambdas, so integer dual values can considerably decrease the initial lower bound. Also, what I observed, and the core computation can be quite, yeah, so when we do this dual warm starts and already compute a good dual vector, we then already have a good direction in which we should aim for cores. The core computations are already much harder when we warm start with dual, because it seems logical. We get closer to the optimum with the lower bound, then we search for a core, and these computations are much harder, and the search may get stuck. While with the original approach, it feels much more oriented and sorted somehow. Okay, next step follows, then we improve up and there and up and there. So the search can sometimes be much faster somehow still. So it's still not clear whether the one or the other is to prefer.
That's actually an interesting point, right? That somehow your lower bound increase is better. Yeah, but in some sense, that making a ridiculously optimistic assumption sort of makes it's when you feed it to the solver, it's like, no, that's obviously not feasible. Here's a core back.
Because it's like it weighs already in a way that we immediately search for hard trade-off solutions. And this is something that makes the initial search already much harder. So, and here the idea is to use something like dual restarts, which is actually enough. Yeah, maybe we just want to recompute the dual vector every once in a while, or maybe include like new constraint that we have learned on the way. Maybe we can do something better. Yeah, because the new dual vector might change again the direction of the core search, and maybe we enter a different direction in order to search for cores that it's easier for the solver. I think maybe once in a while, it's the same restart idea that we have in SAT, basically, just for the dual. So we just change the direction in which we search. Yeah, what needs quantification is, so yeah, can more general cores actually improve the search? So generalized cores. Does the new update rule really need fewer iterations in total? So these are questions that we need to answer. And by how much does the lower bound improve initially, especially when we restrict only to integers? Is it worth it? And these dual restarts actually really help. So this is something that I'm about. Okay, now I also want to finish here because we are already way over time. So the takeaways are really just from this whole talk that cutting plane. So my takeaway is that we should focus on strong LP relaxations. Strong constraints for LP relaxations will create strong constraints down the line. We should try to focus on getting like as strong cuts as possible, preferably according to a quality measure that we introduce. And this dual view on PB optimization is we should like use dual vectors and integrate them somehow in the search. Because it helps to connect constraints in a more global way. And this is something that's completely missing in PB solving because we always just compare key constraints with each other. Dual values make this possible. Okay, some other open problems general in PB solving is that current PB solvers use cancellation, maybe other cuts, but we apply them on CNF, actually boil down to resolution-based solvers very often. So if we have given a CNF, this is pretty bad. We need to get out of this somehow. Yeah? So, and here I want to address again what is a good candidate to separate this and make this improvement is actually click, because I mean it indicates on pigeonhole. It's trivial to generate pre-clicks there. It's just a simple greedy approach. The heuristics already give the separation so that we can have this exponential to polynomial running time. Yeah. So this should be like theoretically examined somehow. whether click actually gives also for other problems like a much better. Yeah, or this is the candidate to actually make CNF or make PB solvers work on CNF much better. Right?
Or just ask for people to encode their problems properly, or maybe not.
Yeah, but yeah, I think there are problems where, of course, for Pigeonhole it's trivial to see this constraint, but for other problems it's not. If you look for stable set problems, for example, or other problems where you have a lot of like conflicting constraints between different entities, you can. I mean, there are many problems in operations research where click constraints actually improve also, and they are not non-trivial to detect like from this pure formulation. Yeah, maybe we can state some theoretical situation.
Thanks a lot.
Sorry for.
No apologies needed. Thank you for a fantastic talk. Any final questions? I mean, we had a lot of discussions during the second half.
At some point, you cited paper of yours on the sorry.
No, yeah, I just cited it as a working paper, so none of this is published actually. So I started, of course, this comparison. I actually wanted to start a similar paper, but now we do it together. So this is gone basically. But this dual guided, so what I presented last is kind of like in a like draft state. So this I want to submit somewhere. I don't know. It's work in progress as a road. None of this is published. But actually, I wanted it to submit it actually already almost 1 year ago, but my computations weren't yet super good because I ran into problems, especially with this. Like, okay, you make the subgradient method, and then suddenly it's super hard to solve somehow. Distorts the search. You need to solve this still somehow to make this like a reasonable approach. Even though the idea is nice, but you still make it computationally. I mean, get some insights. This did not yet work super good, but I will try to solve. So,
Very, very, very interesting. Thank you again. Thank you so much.